Now we're going to move into the next chapter, which is chemical equilibrium. And chemical equilibrium on its own is sometimes a full question, more usually a half question, but definitely comes up every single year. So it's well worth paying attention to this from the very beginning and working your way right through. There's two parts to this section. There's the theoretical part, which we're going to try and get covered this morning, and then I'll give you a few questions to do. And then there's the mathematical part, which we'll spend a little bit more time on. And obviously, it's the mathematical part that will come up more in the exams over the theoretical stuff. Okay, so what is chemical equilibrium? The word equilibrium itself simply means balance. Okay, and as you can see from this diagram here, these two people on this seesaw are balanced. This is one type of balance. This is a balance where the distance multiplied by the mass on both sides is exactly the same. So these two ladies have the same mass. They separate themselves from the center of this seesaw by the same distance, and therefore the mass multiplied by the distance here is exactly the same as the mass multiplied by the distance here, and therefore there is no movement on this seesaw up or down. It's balanced. However, it's what we would call a static balance. Okay, now when we're dealing with chemistry and we're dealing with chemical reactions, they're not static. Okay, chemical reactions move, so we want to take a look at a different type of balance that involves the movement of chemicals towards a certain point. Static balance, as we've said already in this diagram here, same thing, is when you have two masses equally distant from what we call the fulcrum, or the center of balance. And in a situation here, you can see 50 times 10 on this side is 500 newtons, and 50 times 10 here is 500 newtons, which means that if you've got the same force acting on both sides equally distant from the center, you're not going to get any upward or downward movement, and that's what we call static balance. So when this type of balance is achieved, no further motion will take place. That's why we call it static. However, there's another type of balance that I want to look at, and that's got to do with chemical equations that can run backwards as well as forwards. Now, what do I mean by that? Well, let's say, for example, we have A plus B giving you C plus D. So we've got A plus B reacting to give C plus D. But in this unusual situation, when C and D begin to collide, when their molecules begin to collide, they in turn then react backwards to give A plus B. And when their molecules collide, they react to give C plus D. So you can see what happens. We begin to get a cyclic process where A plus B gives C plus D, and C plus D gives A plus B. So you get this non-ending cyclic motion of A plus B to C plus D, and then when they start to collide, they will give A plus B, etc. And we get a cyclic motion, which means in essence that this particular motion is going to be perpetual. It's ongoing. Okay, now how do we show that there are two reactions going on in the one equation, so that A plus B is giving C plus D, but at the same time that C plus D is giving A plus B? Well, we could give another arrow like that here. Okay, and usually what they do in chemistry, they don't use full arrows. Instead, they use two half arrows to show that the chemical reaction is going forward and backward. Now that's the proper symbol. I can't find this on the computer, so you'll notice I'm using two full arrows backwards and forwards, but look, that's only a small thing. That's the proper symbol. So what this is telling me now is that A plus B is reacting through collisions to give C plus D, and at the same time C plus D are reacting together to give A plus B. So this is what we call a reversible reaction. Okay, so that's the symbol, unfortunately, you have to use in the computer, the two arrows going forwards and backwards. But in the beginning, A and B start to react, and there is little of C plus D present in the system. But as time goes on, the concentration of C plus D builds up, and as the concentration of C and D build up, their collisions become more frequent. And as their collisions become more frequent, they then begin to react to give back A plus B, until we reach a stage where the rate of the forward reaction is the same as the rate of the backward reaction, meaning that the number of particles colliding from A and B is the same as the number of particles colliding in C and D. So they're basically producing one another at the same rate. When that happens, it appears that the reaction has hung in the balance, because A plus B are producing C plus D at the same rate as C plus D are producing A plus B. So there doesn't appear to be any net loss of A and B, and there doesn't appear to be any net gain of C and D. They appear to reach a concentration and then hang at that concentration. And once they reach those concentrations where they appear to hang, that's when we say in chemistry that they have reached a state of dynamic balance or dynamic equilibrium. Okay? The rate of the reaction between C and D will continue to increase until it's equal to the reaction rate of A plus B. Now it's very similar to this diagram here. If I have these two taps placed in this position and both are left open, water comes in through the first one. Okay? In the beginning, it'll begin to fill this particular pot. As it fills the pot and reaches the tap, it'll start to flow out. Now if you can picture this, it'll flow out slowly first until the water covers the entire tap, and then it will continue to flow at the same rate as this one is entering. If the rate of entry is the same as the rate of loss, so if the water is coming in at the same rate as the water is being lost, there will be no change in the level of water in that pot. Okay, and when we reach that position, when we get to the stage where the water seems to have settled at a certain height, even though water is being poured in and water is coming out, that's when we say that we have reached what we would call a state of balance. But the balance here is dynamic, because in order to keep that height, I have to keep pouring water in and I have to keep allowing water out. So there's movement in order to achieve this balance. The same with these reactions. A and B are producing C and D are producing A and B. So when they get to the stage where the reaction rates are the same, even though it appears there's no net loss of A and B, no net gain of C and D, we know that the two reactions are still going to maintain that position of balance, and that's why we call it dynamic, because the balance is achieved through motion. Okay, so dynamic balance is a very important term, which you can be asked. Describe the term dynamic balance. It's a balance that's achieved through the rate of the forward reaction being the same as the rate of the backward reaction. So in this case, as it says here, let's go back there, sorry. In this case, the system has reached a state of dynamic balance or dynamic equilibrium. Now, how does that look like in chemistry? Well, take this diagram here, okay? In the beginning, we've got loads of A and B. And A and B are present at a very high concentration, so therefore the reaction rate is going to be quite high. And obviously, as A and B react together, they begin to form C and D, which are at very low levels in the beginning. So the reactants are present at high concentrations, and the products are present at low concentrations. And as A and B begin to react together, obviously they're going to get used up. So they begin to decrease. And as the concentration of A and B decreases, so does its reaction rate. Because we know from a previous chapter that reaction rates and chemical reaction speeds, concentrations I should say, are linked. So the concentration of reactants and the reaction rate are linked. The lower the concentration, the lower the reaction rate. So as the concentration of A and B drops because they're being used up, so does the rate of their reaction. But at the same time, when the concentration of C and D are starting to increase, that means the reaction rate will increase. And A and B will continue to decrease, and C and D will continue to increase until they meet this point here. Now, at that point, we can say that the rate of the A and B's coming together, the rate of A and B being used up, is the same as the rate at which C and D is being produced. Okay, or to put it another way, the rate of the forward reaction is exactly the same as the rate of the backward reaction. And all of a sudden we notice that they reach a flat line. And that flat line is what we call the position of the dynamic equilibrium. Okay, so A and B, they're the reactants. They start to decrease in concentration, so therefore the reaction rate starts to decrease. At the same time as they're reacting, C and D are being produced, and therefore their concentrations are increasing, so the reaction rate is increasing. So A and B continues to decrease, C and D continues to increase until both merge, and then they flatline into a position of dynamic equilibrium. A and B are still reacting, C and D are still reacting. However, because the rate of both the A and B and the C plus D reactions are the same, like that, we get this flat line, which is the position of dynamic equilibrium. Okay. So what is the definition of chemical equilibrium? First of all, it is a state of dynamic balance. So that's a very important word, dynamic balance, a very important phrase, because dynamic balance means they're moving. Okay, so it is a state of dynamic balance where the rate of the forward reaction is the same as the rate of the backward reaction. So it's a state of dynamic balance that is reached when the rate of the forward reaction and the rate of the backward reaction are the same. So just go back to that diagram there in the previous slide. That's what I want you to think of. The rate of A and B is going down, the rate of C and D is coming up until they both match. And when they both match, then we get that state of dynamic equilibrium. So from that diagram, you can come up with your definition. Okay, chemical equilibrium is a state of dynamic balance reached when the rate of the forward reaction is equal to the rate of the backward reaction. So therefore, the word dynamic means that the reactions are still going on. Even though A, B, C and D are still being produced, no increase or decrease in concentration is noted. So chemists will realize when they start a chemical reaction, if it's reversible, they'll know when they've reached dynamic balance, because they'll keep testing the concentrations of everything present in that system. And when the concentrations are changing, it's still adjusting and it's still moving towards equilibrium. But when they realize that the concentrations are flatlined, that there's no further decrease in the reactants and no further increase in the products, then they know that they've hit that flat line, that dynamic equilibrium, where the rate of the forward reaction is exactly the same as the rate of the backward reaction. And that's what we're trying to achieve, and that's what we're looking at in this particular chapter. So the position of equilibrium will remain constant. It'll stay on that flat line unless we stress out the system. Okay, now that doesn't mean that we tell the system, by the way, you're leaving cert exams in a couple of months. That's not that kind of stress. What we're talking about is a physical stress, okay, that we do something to the system. And again, I want you to picture the system as a closed container inside which you put A and B, and it starts to create C and D, and C and D start to feed back and create A and B until we get the concentrations the same and the rate of reactions the same, where we hit that dynamic equilibrium. That's what I want you to think of. Okay, so it's a closed system. Think of a sphere, closed system. You put in A and B, they start to produce C and D. C and D then begin to produce A and B, and their concentrations will flatline. They won't change when they've reached that position of dynamic equilibrium. So how do I stress it out? Well, when the system is stressed, as you see here, the position of equilibrium will move. Now, what does that mean? Well, I want you to take a look at this. Okay, at the moment, you can say that that particular diagram shows a system in balance. Okay, now I'm going to stress it out. Watch. See that? I've stressed it. Why? Because I've upset the position of equilibrium. So what does the system do? The system fights back. And the system says, well, if you've put this stress on me and I want to re-establish a position of equilibrium, I'm going to have to do something in order to reclaim that position of equilibrium. Watch carefully. It moves the position of equilibrium up towards the left-hand side. You see that? Now I'll go through that again. Watch. You start off with a system that is in equilibrium, okay? And then you stress it out. So you move something or you do something. I'll talk about the stresses in a moment. When you stress out a system that is already in dynamic equilibrium, when you stress it out, the balance is lost, okay? And you get a situation like this. Now, you stress it out and the system will immediately respond doing the opposite of what you did in order to re-establish equilibrium. So when you stress it out like that, the system will move its position of equilibrium. Watch the triangle at the bottom. It'll move the position of equilibrium to re-establish that dynamic balance. Okay, so that's what you got to remember again. A system that's in equilibrium, when it experiences a stress, will alter the position of equilibrium to get rid of that stress. Listen again, because that's a definition. A system that's in balance, a system in dynamic equilibrium, when it experiences a stress, will alter the position of equilibrium to neutralize the stress. And in fact, what I'm describing there is what's called Le Chatelier's principle. And Le Chatelier's principle refers to a system in dynamic equilibrium. When a system in dynamic equilibrium, i.e. the rates of the forward reaction is the same as the rate of the backward reaction, and the two of them are going. So when a system reaches a state of dynamic equilibrium and experiences a stress, all right, experiences a stress, the system will alter its position of equilibrium to neutralize that stress. Now I need you to keep that definition in place. Okay, so Le Chatelier's principle, there it is. If a system is placed, if a stress is placed in a system in dynamic equilibrium, the system will move its position of equilibrium to oppose that stress. And that's why I love that diagram in the previous one, even though that diagram shows a system in static balance. It doesn't matter. A system that is in dynamic equilibrium experiences a stress. The system will alter its position of equilibrium to neutralize the stress. That's Le Chatelier's principle. Okay, and we've got to keep that definition in our heads. Now, what are the stresses? The stresses are threefold. Number one, pressure. If you have a system that is already in dynamic equilibrium and you start to change the pressure around that system, i.e. increase the pressure or decrease the pressure, then the equilibrium is going to move. Okay, equilibrium will respond to changes in pressure. If I change the temperature of the system, again, that's another stress to which the position of equilibrium will move. And finally, if I physically change the concentration of any one of the reactants or products, then again, that's a stress to which the position of equilibrium will respond. So there are three things that I can now do to this system that's already in balance to upset the balance. But once I upset the balance, the system itself will re-establish its equilibrium by moving the position of the equilibrium. That's what you've got to remember. And the three stresses are pressure, temperature, and concentration. So consider the following reaction. We've got nitrogen dioxide, which is brown. We've got dinitrogen tetroxide, which is colourless. And both of them, do you see this symbol here? This symbol? Both of them are involved in what we would call a reversible reaction situation. So they can come to a position of equilibrium. Now, this is important over here, and I hope people remember what this means. Delta H equals minus 58.1, meaning that as the reaction forward is going ahead, the change in heat is a loss of 58. So that means that the forward reaction is giving out heat. The forward reaction is exothermic. Now, straight away, what that also means to me is that the backward reaction is endothermic, because the backward reaction will always be the opposite of the forward reaction. Okay. Secondly, the forward reaction goes from brown to colourless, as we're told down here, meaning that the backward reaction will go from colourless to brown. So we're trying to describe the two reactions involved in this system in terms of the heat change and in terms of the colour change. And the question here says, how do changes of temperature affect equilibrium? Now, there are two things I can do here. I can increase the temperature and I can decrease the temperature. So let's just take a look at the first situation. Let's take this reaction here, knowing that the forward reaction is, there you have it, exothermic. Just keep that in your head for a moment. Now, let's stress out the system. Let's increase the temperature and see what happens. If I increase the temperature, what's the system going to try to do? The system is going to try to undo that stress. It always works against me. So if I try to increase the temperature, the system is going to try and decrease the temperature by favouring the endothermic reaction, because endothermic reactions make things colder. All right, and what that means is that if I increase the temperature, all of a sudden we'll notice that the container that has these particular compounds in it will turn dark brown. So an increase in temperature will lead to an increase in NO2, which means that the container will go brown. Okay, now what happens if I decrease the temperature? So my stress, what I'm doing is I'm decreasing the temperature and the system fights back. If I decrease the temperature, the system wants to increase the temperature. And the only way that the system can increase the temperature is by favouring the exothermic reaction. So if I decrease the temperature, I will get an increase in the N2O4 because it will move towards the right hand side, meaning that it will become colourless. So we will be able to see these physical changes in this container as we add heat or as we remove heat. But the key thing we have to do at the start of every one of these questions is to try to figure out which one of the two reactions is the endothermic one, which one is the exothermic one, which one involves a colour change, or if both, what are the colour changes involved in both the forward and the backward reaction. And then once I place a stress on the system will immediately always fight back, and it will alter the position of equilibrium by doing the opposite to what I do in terms of adding a stress. So if I increase the temperature, the system will try to bring the temperature down. If I decrease the temperature, the system will try to bring it up. Okay, so keep that in mind. That's Le Chatelier's principle in action. The system that is in dynamic equilibrium experiences a stress. It will alter its position of equilibrium to neutralize that stress. Now, how does it do that? By fighting back against you. When you stress it out, it will always do the opposite, it being the system. Okay, now there's a video down there, by the way. See that video here? I want you to watch that yourselves because it shows you the brown and the colourless gases being created and formed according to decreases in temperature and increases of temperature. So that particular reaction there is in that video at the bottom, so you can watch that yourselves in your own time. Okay, take this one here. Consider the following reaction. PCl3 plus Cl2 exists in dynamic equilibrium with, see how many words behind that symbol? So those two arrows means exists in a state of dynamic equilibrium with PCl5. Now, how does changing the concentration of Cl2 affect equilibrium? Well, in this case here, no mention of heat, so we don't need to know, because we're not dealing with a stress of heat, so we don't need to know whether it's endothermic or exothermic going forward. That's fine. But what I do need to know is this. The forward reaction involves using these two up to produce PCl5. And the backward reaction involves breaking down PCl5 to create PCl3 and Cl2. Now, if I decrease the concentration of Cl2, that's the stress I'm going to do. So I'm going to start lowering the concentration of Cl2. What's the system going to do? The system is going to fight back, and the system is going to try and increase the concentration of Cl2 against me. So as I drop it, the system tries to increase it, meaning that the equilibrium will move towards the left-hand side to try and produce this Cl2 to replace what I have removed. So if I decrease the Cl2, what's going to happen? The backward reaction is favoured. So the backward reaction is favoured, meaning that equilibrium will move to the left-hand side, and that's what you actually state. Equilibrium will move to the left-hand side, meaning there will be more PCl3 and Cl2 present in the system. Okay, let's do the opposite. What happens if I increase the concentration of Cl2? Now, if I increase the concentration of Cl2, that's the stress that I'm putting on the system. So therefore, what does the system do? The system fights back and wants to lower the concentration of Cl2, and the only way that it can do that is by using it up, getting rid of it. So if I increase the concentration of Cl2, that will drive equilibrium away from the increased Cl2 towards the PCl5, meaning that the reaction moving towards the right-hand side is favoured, and that will see more PCl5 present in the system. Okay, so every stress that we put on the system causes a reaction from the system that is the opposite to what I do. Le Chatelier's principle in action. So let's take this one. Consider the following reaction. Now I chose this one on purpose because this is one we've got to study in detail. We're making ammonia from nitrogen and hydrogen. It's actually called the Haber process. Okay, and we'll come on to the Haber process in a moment, but that's what it's called. The Haber process. It is an industrial application of the addition of hydrogen to nitrogen in order to form ammonia, from which come fertilizers and so on and so forth. So it's a big agricultural reaction. Again, no heat mentioned because we're not dealing with a stress and heat. This time we're changing with a change in pressure. Now I want to point out something here. Pressure will never affect a solid or a liquid. So the one thing you have to make sure, if there's changes in pressure, are all the species in the gaseous phase? And if they are, only then will pressure have an impact on the system. If the species are not in the gaseous phase, then the pressure, no matter what you do with the pressure, nothing happens. So pressure can only affect equilibrium if all species in the system are in the gaseous phase, and please remember that. Now, let's take the two situations again. So you have in this system nitrogen and hydrogen reacting to form ammonia, and at the same time you have the ammonia breaking down again in order to give nitrogen and hydrogen. So you've got the two reactions in there. When I increase the pressure on the system, let's think about this. What's the system going to try and do? If I increase the pressure, the system's going to try to decrease the pressure. Now, the only way that the system can decrease the pressure is if it moves towards the sides that has the least amount of volumes. So the left hand side has 1 volume here, the nitrogen, so 1 and 3. So there are 4 volumes over here, whereas on the right hand side there are only 2 volumes. So if I increase the pressure, what you will always do by increasing pressure is you will force the equilibrium to move to the side that has the smaller amount of volumes. Okay, meaning an increase in pressure here will favor equilibrium moving towards the right hand side, which means you will have more ammonia, which is good for business, because if we're in the business of making ammonia, that's what we want to do. We want to make as much ammonia as possible. So therefore, one of the conditions, in fact, of making ammonia is a high pressure. What happens if we lower the pressure? Well, if I lower the pressure, what's the system going to try and do? The system is going to try and increase the pressure again, okay, because it always fights back. So if I lower the pressure, the system will automatically move to the side where there is the bigger number of volumes, meaning in this case here, it will move back towards the left hand side. So that side will be favored. And that means I will have, call it less ammonia or more N2 and H2, which we don't really want if we're making ammonia. So here we see that pressure only affects gases. So the first thing we've got to do is check and see, are they all in the gaseous phase? Yes, yes, and yes. So now I know pressure will have an effect. If I increase pressure, I go to the smaller side. If I decrease pressure, I go to the bigger side. Okay. So there are the 3 stresses, very simply explained to you in terms of 3 reactions. What does temperature do? If I decrease the temperature, it favors the exothermic reaction. If I increase the temperature, it favors the endothermic reaction. Okay. If I increase concentration, it'll move away from the species that's being increased. And if I decrease the concentration, it will move towards the species. So keep that in mind. And finally then, only if all species and all reactants and products in that system are in the gaseous phase will pressure have an effect. And pressure will have an effect only when they're all gases. If you increase the pressure, you go to the smaller side, and if you decrease the pressure, you go to the larger side. So they're the 3 stresses, and they're the results that are needed in order to follow the position of equilibrium as it changes when a system in dynamic equilibrium is put under a stress. So changes in pressure, as we said already, will only affect equilibrium in the gaseous reactions, and that's extremely important. So you need to remember that well, because they do ask questions sometimes, will an increase in pressure have an effect on this reaction? And people forget that if all the species in the reaction are solids, pressure can't affect solids, nor can pressure affect liquids. Pressure can only affect gases. And if the number of volumes on both sides of a gaseous reaction are equal, then pressure has no effect whatsoever. So in other words, if you increase the pressure and the system looks to both sides to see which one is the smallest, if they're both the same, then there's nowhere for the equilibrium to move to. So keep in mind that pressure only works, number 1, if all the species are in the gaseous form, and number 2, if there's a difference in the number of volumes between the left hand side and the right hand side. So what do catalysts do? Now we already know that a catalyst is something that alters the rate of the chemical reaction, okay? But here's the surprising thing. When we use a catalyst in a system that contains a reversible reaction, the catalyst will speed up both the forward and backward reaction to the same degree. So in other words, if it speeds up A plus B equals C plus D, it's also going to speed up C plus D equals A plus B, meaning that the catalyst does not affect the position of equilibrium. The catalyst only speeds up the amount of time taken to get to equilibrium. Okay, so there are only three stresses: pressure, temperature, and concentration. The presence of a catalyst has no effect on the position of equilibrium, but the presence of a catalyst will allow me to reach equilibrium far more quickly. I hope that makes sense to you. So we can get to that position of balance far more quickly. Doesn't affect the position of equilibrium, but it gets there far more quickly, for the very simple reason, as I've said already, that catalysts will speed up the rate of the forward reaction as well as the rate of the backward reaction, so we can get to equilibrium very, very quickly, which is good for industry. Okay, so let's take a look at this, and we spoke about this already. We spoke about nitrogen and hydrogen giving ammonia, and we told you already it's called the Haber process. Okay, now let's take a quick look at what this is telling me. There's a lot in this chemical equation. First of all, nitrogen and hydrogen are reacting to form ammonia. Okay, the nitrogen, the hydrogen, and the ammonia exist in dynamic equilibrium, so it's a forward-backward situation. The presence of iron is a catalyst to the entire reaction. So that means iron allows this dynamic equilibrium to be reached very, very quickly, which is good. But as the forward reaction proceeds, the heat change is a loss of 92.4 kilojoules per mole. So what that means is that the forward reaction is exothermic. And it's good to write these things down, okay? And what that means also is that the backward reaction is endothermic. So just get into the habit of writing down what the equation is trying to tell you. Now, what am I trying to produce? I'm trying to produce ammonia. So my target is to produce as much of this stuff as possible. So let's see, what conditions would I use in order to drive equilibrium right over to the right-hand side? Well, first of all, the right-hand side has a smaller number of volumes. The right-hand side only has 2 volumes. The left-hand side has 4 volumes. So the very first thing I could do is I could increase the pressure. Brilliant. And by increasing the pressure, you're forcing equilibrium over to the right-hand side to the smaller volumes, which is obviously NH3. Okay. What could I do heat-wise? Now, how could I provoke an exothermic reaction? So in other words, I want equilibrium to move to the right hand side. So I want to favor the exothermic reaction. And if I want the system to favor the exothermic reaction, I have to stress out the system by doing the opposite. I have to lower the temperature. And if I lower the temperature, the system will try to heat that temperature, bring that temperature back up again by again moving the position of equilibrium to the right hand side, and that means I'll have more NH3. So the two things I could do, along with getting the catalyst so that we can get to the position of equilibrium quickly, is to increase the pressure and decrease the temperature. Now, industrially speaking, does that cause any problem? Think about that. Is there a problem caused by the increase of pressure and the decrease of temperature? And the answer is yes. Huge industrial applications. First of all, or I should say implications. First of all, by increasing pressure, that means that we have to reinforce the container. So if you're going to be using very high pressures, you're going to have to make sure the system in which these gases are placed is extremely robust and very, very well fortified, which costs money. Okay, so there's a bit of a problem there. And secondly, if I'm going to lower the temperature, go back to what we talked about when we were dealing with chemical reactions and rates of reaction. The lower the temperature, the slower the reaction. So as I begin to bring the temperature down, I notice that yes, equilibrium is moving over to the side it should be moving over to, the ammonia, but it's doing so very, very slowly. And in industry, time is money. And if time is money, you can't have this delay. So therefore, high pressures cause expense and have to reinforce the system, and low temperatures cause a waste of time because the system becomes very, very slow. So what do? The answer is we compromise. Okay, so I told you already the forward reaction is exothermic. We cool the system, it moves to equilibrium, but cooling the system also slows the reaction down. What about pressure? If we increase the pressure, we'll move to the right hand side, but again, it's costly. So you'll notice at the bottom of both of those slides there, if I just go back to the previous one, a compromised temperature of 500 degrees Celsius is used. Now you might think that's hot, but if you think of the blue flame on your Bunsen burner, that's over 1,000 degrees. All right, so 500 degrees in industry is nothing, absolutely nothing, but it's enough of a temperature in order to make sure that the reaction rate is kept at a decent speed. Okay, it's a low temperature, but it's low enough in order to make sure that the ammonia is produced quickly. We don't want to go any lower than that, or we'd slow the whole thing down. With pressure, for example, as we said already here, pressure has to be increased. But if you increase pressure, that means that you need reinforcement, which is extremely costly. So therefore, we compromise at 200 atmospheres. So the conditions necessary for the Haber process are as follows. A pressure of 200 atmospheres, which is fairly high, so that drives it over to the smaller side. A compromised temperature of 500 degrees Celsius, which is low, but still it's warm enough to keep the reaction proceeding at a good rate over towards the ammonia side. And finally, the presence of the iron catalyst, which gets us to equilibrium far more quickly. Doesn't do anything to the position of equilibrium, but gets us there far more quickly. Okay, so the Haber process, as we said, produces ammonia. Why would a catalyst be used? And I've given it the answer already. To get to the position of equilibrium faster. There it is. With a catalyst, we reach equilibrium far more quickly than we would if we left this thing to its own devices. If we increase the pressure up to about 200 atmospheres, if we decrease the temperature down to 500 degrees Celsius, and we throw in a bit of iron, we get a yield of 17%. You might say that's useless, but 17% yield in terms of industry is acceptable. And that amount of yield, 17%, is harvested then and sold on as ammonia into the, I suppose, the fertilizer industry and the agricultural industry and so on. Very small yield, but again, they're the compromised pressure and temperatures that we have to use. So if you're compromising on temperature and pressure, you're going to have to compromise in yield as well. Okay, and that's the system. That's what we told you already. Nitrogen and hydrogen are added. They're added into the system at 500 degrees Celsius there. Okay, the iron catalyst is present and the reaction takes place, giving me the NH3 that is required, and then any N2 and H2 that's not used up is simply sent back into the system again and recycled. Okay, so it's used over and over again. We call it actually the Haber cycle, but here they call it the Haber process, but that's it. What about H2SO4? I'm just going to do this one then, and I'm going to leave you with some questions to do. The contact process, that's what we call the process of industrially manufacturing sulfuric acid, okay? And again, it's given by a chemical reaction. Now let's study the chemical reaction. We've got sulfur dioxide, gas, and oxygen, gas, giving SO3, gas. So all of these are in the gaseous form, which means pressure will be a stress in this case. Okay, delta H. Now, by the way, delta H always refers to the forward reaction. Okay, because we read from left to right, so therefore the delta H will always be for the forward reaction. What do I notice? The heat change is a loss of 196 kilojoules per mole, meaning that as the reaction proceeds forward, we're giving out heat. This is going to be exothermic, which again means that the backward reaction will be endothermic. Okay, so the forward reaction causes an increase in temperature and the backward reaction causes a decrease in temperature. Now, first question, what conditions of temperature are required? So what do I want to do here? The first thing I want to do is I want to move towards SO3. Okay, so I want to move over to the right hand side. Notice V2O5, vanadium pentoxide is present. That catalyst only gets me to equilibrium very quickly. Now, temperature. Well, let's take two situations. If I increase the temperature, what happens? If I increase the temperature, then the system will try to bring it down by favoring the endothermic reaction and driving the reaction, as you can see here, back towards the left-hand side. Okay, that's not good. I don't want it to go towards the left. So therefore, I'm not going to increase the temperature. I'm going to decrease the temperature. So if I decrease the temperature, what happens? If I decrease the temperature, the system will try to increase the temperature again, favoring the exothermic reaction by moving equilibrium to the right hand side. And if that's the case, then we will have more SO3 present, which is exactly what I want, because SO3 is the first step in making H2SO4. All right. So now we notice that in the contact process, to get over to the right-hand side, I have to decrease the temperature. So we've got the same problem again. If I decrease the temperature, I cause everything to become very, very sluggish. So I can't do that. So again, for the production of SO3, a compromised temperature of in and around the same as the ammonia, about 450 this time, degrees Celsius, is used. What about the conditions of pressure? Well, in this case, if I want to move over to the right-hand side, notice that the right-hand side only has 2 volumes, whereas the left-hand side has 3 volumes. So if I want to move over this way, I'm going to have to try and get equilibrium to move over to the smaller side. To get equilibrium to move to the smaller side, I have to increase the pressure. So an increase in pressure here will cause a movement of equilibrium over to the right-hand side, to the smaller volumes, which means I'll get more SO3 produced. Okay, so it actually becomes quite easy once you think about the stresses you're putting on them, and the key thing, Le Chatelier's principle: when you stress a system, it fights back and it does the opposite. So therefore, again, we've got to increase the pressure. What's the problem? An increase in pressure needs reinforcement in the container. And if you reinforce the container, you have to spend money. So therefore it's costly. So what do? We use a compromise pressure. And in this case, the compromise pressure is just over 1 atmosphere. So just a little bit above normal atmospheric pressure. But it's enough to get the yield of SO3 to be satisfactory. Okay. Why would a catalyst be used? We've said this already. What does a catalyst do in terms of a dynamic equilibrium? It gets me to equilibrium very, very quickly. It doesn't alter the position, just gets me there. So the catalyst will get me there, and then we start to change the temperature and pressure to adjust the position of equilibrium to favor either, in this case here, SO3, or in the previous case of ammonia, NH3. So catalyst does not affect the yield. It affects the speed at which equilibrium is reached. That's extremely important. Okay, and there's your contact process. Now, you don't need to know much about this. You don't need to know the actual procedure, but just enough to say that the SO2 and O2 are first of all turned into SO3. See it there? And then the SO3 then is added to water, H2O, and that gives me out the H2SO4. So at this stage, we add H2O. So we're just bringing the SO2 and the O2 together in order to give SO3. Then the SO3 is reacted with water in an absorption tower, and it gives us out what we call the fuming H2SO4, which is extremely concentrated sulfuric acid. And again, you can look over that in your own time. So I'm going to leave it there. That's enough. There's a huge amount there. You're going to have to go over that video a couple of times and pause and make notes and so on. But I want you, taking into consideration what I've just spoken about, to go to your workbook. Okay, now I'll put the questions of the workbook up for you, just in case you haven't got your workbook at home. But go to pages 47, 48 and work your way through questions 17.1 to 17.3, which is really a practice on how we're altering the position of equilibrium. If any of those questions prove to be any way difficult, you get back to me, send me an email, and I'll send you on the solutions.